This is Lab 2, Charge Tape Revisited. So first is the purpose, and the purpose of this lab was to observe interactions between charged pieces of tape to determine the amount of excess charge on one piece of the tape, and then to simulate these interactions using GlowScript or VPython. And the way we simulated it was to assume that the tapes have their charges evenly distributed amongst its length, and the tapes have equal charges, and we also ignored any air resistance to the moving tapes. So some key concepts are Newton's second law, which is F equals ma, showing that the acceleration is directly proportional to the force. So if there's no acceleration, the net force would be 0. And then the gravitational force, because it's one of the two forces that acts on the tape. And then Coulomb's law, which gives us the formula for electric force, which is also the other force that acts on the tape. So a preview of the results is that the tapes are going to have the same charge and that they will repel each other and that the tapes will be positively charged. And then the final charge was calculated to be 1.6975 times 10 to the negative 8 coulombs. Onto the experiment. This is taken directly from Lab 1. This is the setup of the experiment, and the tape was cut to be 0.33 meters and 0.02 meters wide, and it ended up weighing 0.00033 kilograms. We're going to be looking at the top tape in this experiment, and that one has the electric force pointing upwards and the gravitational force pointing down. And since it does not accelerate, we had F net equals 0, with the system being the two pieces of tape and the surroundings being everything else. Onto the data analysis. So within this experiment, the y component of net force was balanced at 0 because there was no movement in that direction, and we know the two forces in that direction was the electric force going upwards and the gravitational force going down. So we just set up like an equilibrium statement like this and plugged in the formulas using Coulomb's law and the law of gravitation. Okay. And then we solved for Q for the charge, and this is what we got. And this is for what if this was modeled as a point charge like we did in Lab A. So I wanted to keep this number in mind while I use a computational model to model the tapes with the charge evenly distributed amongst its length. So that's what this is. The initial conditions were set here, and this value of Q was altered to estimate once it would be equal to the gravitational force. You can see on the right here the diagram with the arrows. I changed the Q value until both of these arrows looked about the same. But from our calculation with the point charge, I ended up getting this OGQ value down here in coulombs. And you can see here at the bottom, this is Coulomb's law that we used for each like small charge that's distributed amongst the tape. And then we found the field at that place and then add them up together to get the total force. And then here is where we separated the charges and distributed them along the tape length, and then individually found the field at each little charge, and then added them to get the final one, and compared it to the force of gravity to get this Q value over here. So when we modeled it with a uniform charge, the charge on the piece of tape was 1.6975 times 10 to the negative 8 coulombs, but when it was modeled as a point charge, the charge on the tape was 5.9975 times 10 to the negative 9 coulombs. So these values are different. Some potential errors that could have occurred in this experiment was that there was air resistance, on the moving tapes, but we didn't account for that. And also charge could have been lost like while we were handling the tape, so the observed deflection distance could have been different than what it actually should have been, so the charge could have been calculated wrong. So what if we had modeled each of the tapes as a single point charge like in the previous lab? The observations would be different. The charge when you're modeling it with the point charge was smaller than when you're modeling it with a uniform distributed charge. And these estimates do differ, but why do they differ? It's because just the method in which you're calculating it is completely different. Instead of just looking at one spot, you're trying to put the charge on multiple spots at the same time, so there's multiple things that are affecting the final value than just one. So the charge would be we see a little bit different result. And then modeling the charges as evenly distributed along the tape is more accurate to the real world because it wouldn't just be in the center of the tape when the tape is so long. So that was probably a more accurate representation than the point chart. And that's it.